This is Lecture 4, How Neurons Transmit Information, and it corresponds with Chapter 4 in your book, Sections 1 through 3. I won't be covering Section 4, and you don't need to read Section 4 unless you're interested.
Okay, so starting on the lecture material, here in Section 4.1, Electrical Activity in the Nervous System. A little better background on electricity in the nervous system. Stephen Gray, who's considered kind of the father of electricity starting in the late 1600s, demonstrated that electricity could pass through the human body without injuring the individual, and he was famous for this demonstration where he would suspend a kid by insulated cords, so sometimes like silk cords, and create static electricity near the boy's feet, and show that foil and little bits of paper were attracted to the boy's face. So the static electricity passed through the boy's body to attract these bits of paper and foil near the face. A bit later, Luigi Galvani showed that electrical stimulation created muscle contraction in frogs' legs, and one of his experiments involved stringing up these frogs' legs on his, I think, the ceiling of his building during a lightning storm, and letting the electricity in the air stimulate the frogs' legs to move. A little bit after this, Fritsch and Hitzig showed that electrical stimulation of the neocortex can cause movement, and they showed this in animals. And after that, Bartholow showed that the brain of a conscious human can be stimulated to produce involuntary movement. He showed this during surgery of a live person. And then Caton came up with the voltmeter, which is a device that measures the flow and the strength of electrical voltages by recording electrical potential differences. So it's kind of a very early and basic level device for measuring electricity. And he used this voltmeter to measure electrical flow in the brain, so directly showing that there was electrical flow happening in the brain. And this laid the groundwork for the modern encephalogram, or EEG, which you might recognize. It's this way of measuring brain waves where you have these sensors, typically embedded in a cap, that are connected all over the head and measure neuronal activity underneath, and you get these nice recordings, these kind of like wiggly recordings. It's one way to measure like seizures or really basic broad processes. Just a side note, in case you're interested, there are actually video games that you can play these days using EEG. So there's some different types of brain waves that you can control consciously. One example would be called alpha waves, and we'll talk about this later when we talk about sleep and consciousness. But alpha waves can be controlled by relaxing or concentrating. And so there's some really basic EEG caps or sensors that you can buy, and they're connected to brains. So there's this game you can buy on Amazon, actually, where you control a levitating ball with your alpha waves. And then some labs, this is not available for commercial use, but some labs, I think, in Barcelona have created like a system where you can play World of Warcraft and two-player Pong and things that are a little more complex using EEG signals. And this is called brain-computer interface, when you use signals from the brain to control a computer. It's an area of research that's becoming more and more popular, and they're coming up with more and more ways to use it. So another way that people are trying to use EEG is by creating music through brainwaves. So if you're interested in music or music therapy, this could be interesting to you. There's one example of scientists teaching people who can't move to use their brainwaves to create drum beats. And it's a difficult process, but they're still kind of in the development for it. There's another example of people who can control the tempo, dynamics, and articulation of existing music through EEG. And then this is I hadn't heard of this actually before I was looking these things up for this lecture, but apparently there's these cat ears that you can buy that also rely on maybe alpha waves to control the orientation of these cat ears. Okay, so back to the course material. Helmholtz discovered or hypothesized, I suppose, that the signals in neurons are too slow to be just using electricity. And a bit later, Bernstein figured out that it's a wave of charge that passes from neuron to neuron rather than actual ions passing through from neuron to neuron. And he discovered that chemical signaling allows messages to travel along the neuronal axon and pass the message to the next neuron. Some ways that we can measure activity of individual neurons include inserting a microelectrode, which is a very, very small microscopic insulated wire or a tube filled with like salty water whose uninsulated tip is used to stimulate a record from those neurons. And an oscilloscope is a device that records changes in voltage over time. It's like a very sensitive version of a voltmeter, and EEG is like a bunch of oscilloscopes that record different that record the activity at a bunch of different sensors. Okay, and then Hodgkin and Huxley were very famous scientists who studied the axons of giant squid. Giant squids have these very large axons that make it easier to study them because they're so large. And they use these giant squid axons to understand electrical activity within the neuron. They received a Nobel Prize for this in 1939. And they identified the nerve impulse, which is this change in ion concentration across the cell membrane that underlies signaling between cells. They found out that the electrical activity in a neuron is caused by movement of intra and extracellular ions carrying positive and negative charges across the cell membrane, and that changes in the concentration gradient of these ions creates changes in the voltage gradient. And this is what underlies this cell signaling, and so that's what we're going to talk about for pretty much the rest of this chapter is this basic process.